Hi viewers, this is my today's presentation. Hope you are enjoying my videos and I am also getting little wiser every day with you. So let us start. So today I am going to discuss alternating currents, then phasor diagram, then series LR, CR and LCR circuit. First, alternating current. Why we need alternating current? This is all about power transmission. High voltage, low current, low heat loss during transmission. Now, this is the circuit symbol of AC generator. When a conducting loop is rotated with angular frequency omega in a magnetic field, a sinusoidal voltage is induced in that loop. And we call this V equals to V0 sin omega t. Correspondingly, current I equals to I0 sin omega t. And frequency, angular frequency omega equals to 2 pi f, where f is the natural frequency of that element. And time period t equals to 1 by f. Also, t is related with angular frequency, t equals to 2 pi by omega. So these are all the tools which we will apply in circuit analysis with AC, right? Before going to the circuit analysis, we will study peak value, average value and RMS value of the current and voltages. So we have the sinusoidal voltage and current V equals to V0 sin omega t, I equals to I0 sin omega t. The average value of current, I average with one cycle. So for a full cycle, we will find this current, average value of the current, and this is 0 to t I dt by 0 to t dt. So we place I as I0 sin omega t. Now this sin omega t over a full cycle leads to 0. Okay, so full term is 0. So average value of current or voltage over a full cycle is 0. So we calculate average value in a half cycle. So half cycle means time period is half. So this reads 0 to t by 2 I dt by 0 to t by 2 dt. We put this value I0 sin omega t and this sin omega t, this time with very simple calculation we will find this 2 by pi times I0. Okay, so we get the average value of current is 2 by pi times the peak value. So average value is 2 by pi times I0 or 0.637 I0. Similarly, for voltage, average value is 2 by pi V0 or 0.637 V0. Now we will calculate RMS value. So full form of this is root mean square value of current or voltage. To find RMS value, we will start from the square, then mean, then root. We have the sinusoidal voltage and current V equals to V0 sin omega t, I equals to I0 sin omega t. To find first square, I square equals to I0 square sin omega t. Now mean over one cycle, I square over one cycle, 0 to t I square dt by 0 to t dt. 0 to 2 pi by omega I0 square sin square omega t dt by 0 to 2 pi by omega dt. And with a simple calculation, it comes to I0 square by 2. So this is the square average, right, of sinusoidal current. Now root, this is the RMS value, first square, then mean, then root over. Okay, so I square average over one cycle. And this value is I0 by root 2, almost equal to 0.707 I0. So just we completed the basic terms in analyzing circuit. Also the VRMS V0 by root 2 equals to 0.707 V0. Now the comparison of peak value, RMS value and average value. Clearly we see the peak value I0 is greater than RMS value greater than average value. Okay. Now form factor. This is a very important term in circuit analysis. Form factor is defined as RMS value by average value. Okay. We get RMS value for the voltage V0 by root 2, average value 2 by 5 times V0, and if we divide these two we get form factor as 1.11. So this is the form factor. Now let us solve a problem to be more clear with peak value, RMS value, average value. I find peak value, average value and RMS value and frequency of the current I equals to 5 sin 300t minus pi by 4. So its solution, we will compare with this standard equation I equals to I0 sin omega t plus minus pi. After comparing we get what? This I0 is equals to 5 ampere, right? And average value is 2 by pi times I0, and this simple calculation 3.18 ampere. RMS value is I0 by root 2, and substituting this value we get 3.535 ampere. When we compare omega t with 300t we get omega equals to 300 radian per second. Correspondingly the frequency omega by 2 pi is 47.75 Hz. Now I want to say here, in India, in our country, the domestic supply frequency is 50 Hz. Okay, 50 Hz. Now phasors. What are phasors? We represents voltage and current as rotating vectors. I1 I0 sin omega t, and this is a phasor diagram. What is this arrow indicates the magnitude, and this is the angle omega t. When it rotates counterclockwise it leads, okay, and when it rotates in clockwise it lags. The phasor may be represented like this also, where I0, this component is cos component I0 cos omega t, and this component is I0 sin omega t. We can choose any one of them, right? So why we study phasors? To simplify circuit analysis using graphical construction, so it will be more clear in later sections. So let us study first. Now we will study resistors, capacitors and inductors in AC circuit. So these all are circuit symbol. We will use this in the following sections. So resistor in AC circuit, this is the circuit diagram. I equals to I0 sin omega t. So the voltage drop across this resistance VR equals to I times R, equals to I0 R sin omega t. So VR equals to V0 sin omega t. We replace I0 into R by this V. Now here I0 and V0 both I and V are in phase. Very clear from this picture, also from the phasor diagram. So this arrowhead represents both voltage and current, as this is represented by single arrow, but their magnitude is different for the voltage and for the current. So there is no lag or lead between current and voltage for passing through the resistor. So current and voltage are in phase when it passes through the resistor. Now we will study capacitor in AC circuit. So the circuit diagram, Now Q equals to C times Vc. Vc is the voltage across this capacitor, equals to C V0 sine omega t. Okay. Now correspondingly current I equals to dq dt. So simple derivative of this quantity is CV0 is constant, sine omega t is cos omega t, and this omega comes out. Okay. Now we will call this term as I0. I equals to I0. Now this cos is represented as sine, this sine omega t plus pi by 2. We can represent cos omega t by sine omega t plus pi by 2. So comparing these two equations, we get there is a phase difference of pi by 2, right? Keep in mind. Now here we represented V0 as I0 by omega c, or I0 equals to V0 omega c. So capacitive reactance, a new term here, we call this Xc equals to 1 by omega c. Okay, this is called capacitive reactance. And this is the diagram of current, voltage, sinusoidal current and voltage. We clearly see that current and voltage are not in phase. Okay, so to be more clear, we see the phasor diagram here. This vector represents the current, this vector represents the voltage, and clearly we see a phase difference of pi by 2 or 90 degree. So forget all of these things, just see this circuit and this phasor diagram. So we clearly analyze this circuit with the help of this phasor diagram. So this is very important in alternating circuit analysis. That's why we use phasors, right? So in current passing through the capacitor, current leads the voltage by pi by 2. So current leads the voltage by pi by 2, right? This is also clear from the phasor diagram. Now inductor in AC circuit, this is the working diagram. So voltage drop across inductor VL equals to L di dt. So L I0 omega cos omega t, and VL equals to V0 sine omega t plus pi by 2. Again we replace this cos by sine omega t plus pi by 2. Okay, and this V0 is what? This L I0 and omega, right? This term L I0 and omega. So V0 equals to I0 times omega L, or I0 equals to V0 by omega L, and I equals to V0 by omega L sine omega t. So inductive reactance is 1 XL equals to omega times L. This is the diagram representing current and voltage, sinusoidal current and voltage. Clearly we see voltage is leading the current. More clear in phasor, right? Again, this vector represents the voltage and this vector represents the current, right? So current here lags behind the voltage. Again, voltage leads pi by 2 than the current because it is in anticlockwise direction. So in inductor, voltage across inductor leads the current by pi by 2. So here voltage wins, right? But for the capacitor, current wins. So resistance or reactance versus angular frequency. So this graph tells everything about AC circuit. What? This horizontal axis represents angular frequency. When we increase angular frequency, there is no change of resistance, right? So in resistive circuits only, there is no change with change in angular frequency. But for a capacitive circuit, what we see, the capacitive reactance gradually decreases, right? It gradually decreases with increasing frequency. Very difficult to write with mouse. And for inductive reactance XL, it increases with frequency. Okay, so this is all about circuit analysis. Hope you enjoyed this video. Thank you.